Okay, let's do an example from, I just made this up, but this one's like in section 4.3, where we have some relatively complicated function here. And without Desmos, without a calculator, we want to be able to graph this thing super accurately without actually plugging in numbers and just saying, okay, x equals 1, x equals 1.1, x equals 1.2, which is what a graphing thing does. Let's just figure everything we can using calculus to be able to graph this function. Okay, so the first thing we want to do to graph it is figure out what the slope is doing, where it's going uphill, where it's going downhill. And the easiest way to find that is where it switches over, where the slope is 0 or where it's infinite or something, and that's the critical numbers. So step 1, you find the critical numbers, which is where the derivative is 0. So first we take the derivative. Derivatives here, oftentimes here now the derivatives are kind of easy because we're dealing with kind of simple functions. So the derivative is 4x cubed, see 3, that's minus 9x squared. Derivative 2 is 0, so that's our derivative, and we want to know all the interesting points of this function, which is typically what they call the critical numbers, where the derivative is 0 or infinite. Now we don't have any infinities here, no sharp points, no weird stuff going on. So we set that equal to 0. Where is it 0? Well, obviously x equals 0 works, right? So x equals 0 is one answer. Now that we get x equals 0 as 1, now let's look at the ones where x isn't 0, which lets us divide by x, because we can't divide by 0, but now we're saying for everything not equal 0, let's divide by x. I can divide by x squared actually, right? Take out an x squared. If I do that, I have 4x left here and only a 9 there. So the other critical number is where this is true. So let's see, that's 4x is equal to 9, or x is equal to 9/4 or 2.25. So those are the only interesting places in this curve where interesting things happen. Let's find those points though, right? Those are the x values. So when x equals 0, y, or our function, we plug in 0 here, we get 0 minus 0 is 2, y equals 2. So one point is 0, 2. Now when x equals 9/4, y is equal to, okay, this one's trickier. You can plug this in a calculator, which is what I'm going to do. 9/4 is 2.25, so y is 2.25 to the 4th minus 3 times 2.25 to the 3rd plus 2. And so let's get that number there using a calculator. 2.25 to the 4th plus, let me do that one first. 2.25, yeah, a lot of calculator work here, to the 3rd times 3 negative plus 2.25 4th plus 2. I get negative 6.54. Pretty ugly number, goes on forever. Negative 6.54. So our other point is 9/4 or 2.25, and then it's not pretty, negative 6.54. Okay, so those are our two interesting points. I'm going to circle them so remember them. So we want to know what happens on each side of those points. So if we have our graph here, something interesting happens at 0, and something interesting happens, actually let's plot the points. So 0, 2, so that would be somewhere around here, let's say 0, 2, x equals 0, y is 2, and then x is 2.25, if that's 2, 2.25 is like this, and y is negative 6.54, oh no, that's way the heck down here. So that's something like this. Okay, so those are our two interesting points. So what we want to know is on this side, is it going up or down? And in between, is it going up or down? And over here, is it going up or down? And since these are the critical numbers, we know that that's where the interesting things happen. So on either side, it's going to be pretty uniform. Whatever's happening here is going to be happening here forever. Okay, it's not going to change, or we would have gotten another critical number. Okay, so to know if it's increasing or decreasing, now we got to plug in numbers. We got to plug in a number over here. We got to plug in a number here and plug in a number here. Okay, so we got to plug in a number less than 0, in between 0 and 2.25, and then bigger than 2.25, and see what the slope is doing on each side to know if it's increasing or decreasing. So again, that's just what we have to do. So our slope is 4x cubed minus 9x squared. Let's plug in a number on this side of 0, like -1. Choose the easiest numbers. So at -1, you get, that's negative, so it's -4. Negative, yeah, because it's cubed, -1. And then minus, that's just x squared, -1 squared is 1, so minus 9, -13. So the slope is negative, so it's decreasing from negative infinity all the way to x equals 0 on this interval. It's decreasing, so I'll just say something like that. It would be decreasing because the slope is negative. Now, how about in between 0 and 2.25, right? In between there, that's the other place. So between 0 and 2.25, what is the slope doing? So we choose an easy number like 1. Plug in 1 here. We get f prime of 1. Where should I do this math? I'll do it right underneath here. F prime of 1 is 4 minus 9. 4 minus 9. So that's also decreasing there. So it's negative. So 4 minus 9 is -5, which is negative. So it's also decreasing there, which means we have a slope of 0 here, but it's decreasing on either side, which means that's one of those weird inflection points thing. It's always negative right there. So when we graph that, that's how we know how to do it. Now let's look at the only other interesting point, greater than 2.25. So let's plug in 3. So when x equals 3, so in between 3 and infinity, we only have to look at, find the critical numbers again, and then just go in on one side of the critical number, in between them, and then on the other side. So just 3 points here. So 3 to infinity, we plug in 3. Let's see, that would be 4 times 3 cubed minus 9 times 3 squared. 3 times 3 times 3 is 27. 4 times 27, I can do that in my head. I'll do a calculator. 4 times 27 is, 108. 108 minus 9 times 9 minus 81. Okay, that's clearly positive. That is, and we don't need to know the number. All that matters is it's positive, so it's greater than 0. So here it is increasing. It's going uphill. Okay, so right away we know that it's decreasing here forever. Slope is 0. Still decreases to right here. Oops, sorry, shouldn't have put a point there. Still decreases all the way down to here where the slope is 0, and then it increases from there on up. So that's what our curve is going to look like. Because we know the slope is positive, slope is negative, slope is negative, slope is 0 here, so this is an inflection point. Now right away we could probably tell some interesting things, right? Like it's concave up here, concave down here, concave up here. But we don't know for sure, so then we got to do some more tests. Okay, we found the local minimum maximum values. Just from graphing this, there's only one, right? There's only 2 places where the slope is 0. This is not a local minimum. Clearly this is a local minimum because the slope, we just figured out, the slope is negative here, slope is positive here. So we know that, and that point was 2.25 negative 6.4, so 2.25 negative 6.54 is a local min. From drawing the graph, we know it's the global min. It's not only locally the smallest, it's the smallest this graph makes, right? Because we know it goes positive forever here. It goes negative forever here. It keeps going up, it never dips down again. So we know we found the overall, the smallest it is, which is like y is negative 6.54, is the global minimum as well as a local minimum. Lots of definitions here you got to keep straight. All right, now find intervals of concavity, inflection points, and those are places now where maybe we can use the second derivative to tell us some interesting things. Okay, so let's look at the second derivative here. The first derivative we already figured out was 4x cubed minus 9x squared. The second derivative then, again these are easy derivatives, is 3 times 4, 12x squared, 2 times 9 minus 18x. And again, what we want to know is first when that's 0, and then when it's greater than 0 and when it's less than 0. Okay, those are the interesting places where it's greater than 0, when it's less than 0. Okay, so first off, let's figure out when that's 0, and that's always interesting. That's where typically if it's a nice smooth curve, that's an inflection point. So we set that equal to 0, and obviously x equals 0 is a solution. And now we divide by x, and then we get 12x minus 18 equals 0. And so let's see, that would be 12x is equal to 18, or x is equal to 18 divided by 12, which is what? Divide up 3 halves, which is 1.5. So there's another inflection point at 1.5. Okay, in my very bad picture here, and you should do a better job than this one. Here is 2.25, right? That's 2.25. Here's 0, so 1.5, somewhere in here, it switches over from getting steeper and steeper downhill to less and less steep. Okay, so that's that inflection point. So from there to forever, it's concave up. From here to there, it's concave down, getting more and more steep, and then less and less steep. That's what inflection points do. And here it's getting more and more steep in the negative direction, so here it's concave up, concave down, concave up. And there's only 2 inflection points, so it only switches over twice. Right, it switches over here and then here. From concave up to concave down to concave up. Okay, so that's one thing that's kind of cool. We found the inflection points by setting the second derivative equal to 0. And again, that works on nice, well-behaved functions. It doesn't always work. You can have inflection points where the second derivative isn't 0. But if it is 0 in a nice function, that's typically an inflection point. But again, the definition of an inflection point is where it switches over from concave up to concave down. So really what we need to do then is figure out on either side of those points, is the second derivative positive or negative? If the second derivative is positive, it's concave up. Second derivative is negative, it's concave down. So that's what we really have to do. So let's look at that. We have 0 and 1.5. So we need to figure out a number here, a number here, and a number here on each side. What's the second derivative? Just like we did for the first derivative. So you choose the easiest numbers. So let's choose this one here. Let's say it's -1. Let's choose 1, and let's choose 2. Okay, so what's the second derivative of -1? And again, this should be easy math. Plug in -1 here. That would be 12 minus 18, but it's -1, so plus 18, which is 30, which is greater than 0. Therefore, we know that it's concave. That's concave up. If the second derivative is positive, it's concave up, which we figured out there, right? -1 is concave up. So this is how we prove it. Okay, second derivative at 1 would be 12 minus 18 here. So it would be 12 minus 18, which is -6, which is less than 0. So it's concave down there. So we know everywhere here it's concave down, which we knew anyway. And then, how about 1.5? So, no, sorry, how about 2? On the other side of the inflection point there, that's 2. So the second derivative at 2, again, easy math, kind of, that's 2 squared is 4, so that's 24. Minus 36, which is clearly negative, which is, wait, I didn't do that right. 24 times 4 is 48. 48 minus 36, which is positive 12, which is greater than 0, so it's concave up, which again we knew from my really bad picture it's concave up. Okay, so that's how we can use the second derivative. We could find inflection points from it where it switches over from concave up to concave down, And we know if it's concave up or concave down by choosing easy points in between the inflection points and seeing if it's positive or negative in those points. Now, if you know all that, know all these things, we can sketch a better picture of the graph. But, you know, this is a good rough sketch. And then you can plug it in on Desmos, which you're welcome to do. Just, you know, you can't do that in a test, and see how closely your graph matches the real graph. And you can get really, really close. It's pretty cool how well this stuff works. All right, that's an example from 4.3. It's all about taking the first derivative, second derivative, setting them equal to 0, looking at all those definitions. It can take a lot of, you know, each problem can be a lot of work. It can take a whole page, then you want to sketch the graph as best you can. So you just got to take your time and work on these, and then always check with Desmos and see how well you did. Okay, thanks for listening.